right. Can you guys hear me? Yeah? Okay. So is everyone happy with their midterm grade? It's nice to see some of your faces. All right, well, let's get started. So I will be giving you the lecture today, and we're going to be talking about reinforcement learning in the brain and the computational role of a neurotransmitter called dopamine, which I'm sure all of you have at least heard about. Okay, so just a brief recap. On Monday, we talked about how reinforcement learning is about learning the value of states and corresponding actions to maximize the amount of reward received by an agent. Okay? And today, we're going to ask the question, how does the brain implement these learning algorithms in real neurons? And what is the neural substrate of learning from trial and error? All right, so the objectives is to understand how the brain implements these algorithms to learn by trial and error. And then at the very end, we're also going to talk about what happens when these learning algorithms go wrong in disease. I like to lecture interactively, so if you have questions, please jump in, and I'll also be throwing questions at you. So, all right, let's jump in. So, who here has heard of dopamine? All right, can someone sort of blurt out what they have heard about dopamine? What does it do?
It makes you feel happy.
Makes you feel happy. Good. Okay. Anything else? Yeah.
It's a catecholamine which drives the reward system in the brain.
All right, it's a catecholamine, drives reward processing in the brain. Exactly. So dopamine is a neurotransmitter produced in the midbrain here in these two structures. One of them is called the ventral tegmental area, or the VTA. And the other one is called the substantia nigra pars compacta, or abbreviated SNC. And that's the molecular structure of dopamine. And here is a picture of the axonal arbors of dopamine, and they're very far-ranging, and they synapse onto many different areas of the brain, right, up to the prefrontal cortex, other structures in the basal ganglia, emotion centers like the amygdala, and etc. So dopamine wears many hats, and it's involved in actually very many processes. So dopamine plays a role in motivation, learning, action selection, addiction, schizophrenia, Parkinson's disease, etc. But one reason that dopamine is so highly studied is because of a very, very special discovery made exactly at the intersection between machine learning and neuroscience. And that's what we're going to focus on today. But first of all, let's sort of dive into this concept that you guys talked about, that dopamine is the happy or the pleasure hormone. All right, so what are some pieces of evidence that dopamine plays a role in processing and distributing information about rewarding events? So back in 1954, these two scientists, Olds and Milner, did these experiments where they basically hooked up an intracranial electrode into the medial forebrain bundle deep in the mouse's brain, or a rat's brain. And the rat could press a lever to basically electrically stimulate its own neurons. And they basically observed the behavior of this rat and found that it basically just, the more it pressed, or when it started pressing, the more it would press. And it seemed to really enjoy pressing this lever and exciting its own dopamine neurons, or midbrain neurons. They didn't know it was dopamine back then specifically, but and I thought this quote was pretty funny. The control exercised over the animal's behavior by means of this reward is extreme, possibly exceeding that exercised by any other reward previously used in animal experimentation. So it's saying that this rat was so energized to press this lever, more so than it would for food or anything else. Okay, so that was back in the day. It was pretty imprecise stimulation of neurons, but nowadays we have more precise techniques such as optogenetics, which is a method of exciting neurons using light. So you'd implant these optical fibers deep into the brain and then flash light, and you basically excite neurons. All right, so that's one piece of evidence, right? So these brain areas that contain dopamine neurons, they're the best targets for this intracranial self-stimulation. And rats want to press these bars really quickly to excite themselves. Furthermore, if you treat these rats with dopamine receptor blockers, they actually learn less rapidly to press a bar for any reward, particularly food. And the third piece of evidence, there are lots of pieces of evidence, but these are just three. The third piece of evidence is that drugs like amphetamine and cocaine are addictive in part by prolonging the influence of dopamine neurons. All right, so these are just some pieces of evidence that might go to show that like dopamine is just signaling pleasure or reward. But because we're good scientists, we want to test every hypothesis that we have. So it might not just be as simple as that, right? So here our question we want to ask is, does dopamine just signal reward? And a plausible hypothesis is that if dopamine signals reward, we should expect dopamine release whenever some kind of reward is being presented, right? That would be pretty consistent with all the pieces of evidence I just told you about. Okay, so I guess if you didn't read that, how might you design an experiment to actually test this hypothesis? What would you guys do?
Maybe present different kinds of reward and see if dopamine is released?
Good, very basic, yes. Present lots of reward, see if dopamine is released when reward is released or presented. What else would you present as like a control to see if it's not responding to other stuff?
Don't present any reward and see if dopamine just naturally rises and falls.
Very good answer. Right. See if there's any natural fluctuation that's not triggered by any external reward. Anything else? All right, maybe one more thing you might consider is to present different sensory stimuli, right? So like lights or flashes, or even just presenting the lever, right? So you want to make sure that it's actually the rewarding thing that releases dopamine and not just a stimulus out in the world. All right, so like we just said, we can present reward to animals and record the responses of dopamine neurons. So that's exactly what Schultz, Diane, and Montague, these three scientists, did back in 1997. So here you see plotted is a raster plot of each spike from a neuron's activity. And these are a bunch of neurons here plotted. And then on the top is kind of like a histogram sum of these spikes over time. So you can see where there's a lot of density in action potentials in spikes. This creates like a dense histogram plot, right? Yeah?
Wait, so is dopamine a chemical, or is it a neuron, or is it like both?
It's a neurotransmitter, yeah.
Okay. Wait, what does that mean? So does it go into a neuron and make it fire?
Exactly, yeah.
Oh, okay.
Yeah. All right, so here reward is being presented right here. And then you can see subsequently there's like a burst of firing in these dopamine neurons. So that would seem pretty consistent with our hypothesis, right? All right. Now, what if I told you that, like I said earlier, maybe we should present different kinds of stimuli and then also reward to make sure that it's actually specific to reward, right? So what a lot of people do, especially in what we call classical conditioning paradigms, is to have a stimulus or a cue, and this is usually called the conditioned stimulus, the CS, to have that come sometime before the reward, okay? So this is kind of like if you've ever heard of Pavlovian, as you talked about on Monday, Pavlovian conditioning. It's like when you ring a bell, and then that predicts that the food is going to come, right? So the dog starts salivating when they hear the bell after they learn. So same thing here. You present a cue, which can be a sound or a light flash. And what happens here over time is if you present a cue and then follow it by reward, after a bunch of learning, the dopamine neurons actually start to fire right after the cue and not at the reward. So you might say that's pretty interesting. What's going on here? This sort of contradicts our hypothesis that dopamine only responds to reward. Now, a third piece of evidence is seen here, where there's a cue being presented, and then in these trials, they're called omission trials, they actually take out the reward and see what happens. So if you take out the reward, suddenly the dopamine neurons start to stop firing, like they fire below baseline, because baseline, there's still some random fluctuations, right? And this is super interesting because it's almost like, I kind of expected reward, and then it didn't come, and then now I'm disappointed, right? So this is another piece of evidence that makes this situation really interesting and makes us ask, what is dopamine actually reporting here? So does anyone have any guesses?
You said like desire, like anticipation.
Uh-huh. Good, that's getting close. So anticipation. Other guesses? Mm-hmm.
Expectation, maybe?
Great, expectation.
Wanting.
Wanting? Okay. Wanting is kind of like a more amorphous term, but I think these are all of a similar concept. And I would say it more that it's like prediction, okay? So I'm like predicting that there's going to be something that's coming. And if my prediction is wrong, then maybe my dopamine neurons change their activity. So actually, this is called a reward prediction error. And the reason it's called this is because what a reward prediction error is the difference between the actual reward and the expected reward. So let's just look at these three examples. So here, if you look at the reward being presented, we can just sort of give it a number for now. So let's say the reward has a value of 1, okay? So first of all, in this top plot, I didn't predict reward at all, but it came, right? So the actual reward was 1, but what I expected was 0, right? So my overall reward prediction error is 1, right? So it's positive. All right, in the next trial, I see that I did actually predict the reward with the cue, and my reward was also 1. So what would my reward prediction error here be? 0, great. And then now here I predict a reward, but my actual reward was 0. So what is my prediction error? Negative, exactly, perfect.
So then why would you have a spike right after your cue?
Because your dopamine neurons are communicating a prediction, right?
So like when you're using your RPE to measure sort of the predicted activity of your dopamine neurons, when do you apply that? Like at the moment of the reward? Is this RPE applies at the moment of the reward and nowhere else? Is that correct?
Well, so the RPE is a function of time. So you can predict it. You can predict the activity of dopamine neurons at every moment in time.
So let's say I would apply the RPE at time equals whatever time you apply the cue.
Okay. Yeah.
Then why would you expect there to be a spike? Because there's no actual reward at that point, right?
Great question. We're going to talk about that. All right. So now we found out that dopamine reports something called a reward prediction error. Okay. So now we're going to try to have a pull everywhere. Okay. So this is sort of like just an open-ended question here. There's no multiple choice. I like open-ended. So I just made a different link because the other one's Venki's. But think about this. Why would the brain want to predict the future as opposed to just react to the past or react to what's happening right now, right? So why do you think dopamine neurons are predicting the future? More interesting, okay. Why are they predicting the future as opposed to recording what's happening right now in the present? All right. Hunting. Habit. Not sure what that means, but okay. Helps with learning. Okay. To prepare for danger. All right, I like that answer. Future actions, outcomes, anticipation. So a lot of the times people say that the brain is a prediction machine, right? You're always trying to predict what's happening in the future in order to better understand your environment and what is actually happening in your environment, right? Right, these are good. Uh-huh.
So I was wondering, in the case where there was no prediction but the reward still occurs, there is still a dopamine level. So how is it that it is a prediction only when it was almost like a surprise? There was still dopamine released when there was like a surprise.
Yeah, so that's why it's not exactly, I wouldn't say dopamine is a prediction, it's the prediction error, right? So it's like the discrepancy between the actual and the expected. Yeah. Great. All right, so now we've seen this in the experimental on the experimental side, but why does this relate to this machine learning algorithm called temporal difference learning? So Menki briefly covered this on Monday, and I'm going to go into it as an application of this particular problem. So what's really awesome about this is that TD learning was actually developed separately by machine learning scientists who were studying things like optimal control and how do you learn things, right? And it just so happened that when they saw this piece of data, they were like, oh, it looks really similar to this thing called temporal difference learning that we use in machine learning. And just a very brief review of this, of what TD learning is, you can think about the environment as having states. And these states, at least in this particular example, you can think of as time steps. Okay, so right now at time t, I'm in state t, and then in the next time step, I'm in state t plus 1. Okay. And then what is value, right? Value is the discounted sum of all future rewards, right? So all the future rewards I'm going to earn, I just add them all up. And this is how you would express this in math. And this gamma here is a discount factor, which means that it tells me how much I'm going to care about rewards in the future, right? So if it's high, then it means I actually care about what's going to happen in the future. And if it's low, then I only care about right now. And so if you write this sum all out, what you get is the reward at this time point plus the reward at the next time point times this discounting factor plus the reward at t plus 2 times this discount factor squared, et cetera, right? Now, if you look really closely, you can see that you can actually simplify this part of the equation to just be gamma times the value of the next time step, right? Because the value of the next time step is just this term, but with t plus 1, right? So this value actually reduces just to this particular equation, the value at this particular time point. And now you'll see where the actual temporal difference prediction error equation comes from. Because what this is actually saying is this is the prediction, or sorry, this should be equivalent, right? The value at this time point should be equivalent to the reward at this time point plus all the future rewards, right? But if there's an error in my prediction, right? If my value at this time point doesn't equal this, then that's going to be my error. So what happened in this equation is that I basically just took the v of t and subtracted it on this side, right? Simple. And so what you do with this error is telling you, oh, your prediction's actually wrong. You better update your prediction so you have the most accurate internal sense of what's going to happen in the future. And so what you do with this error is you can use it to then update your current value, right? Because the goal is to get your value to match, of this time step, to match the reward plus the future.
Wait, what is v hat?
Oh, v hat is just a prediction of the reward. Because you have to learn that. You don't know the value at this time point.
Then shouldn't the error be the prediction of the future value minus the current value? So like rt plus gamma v hat t plus 1 minus just vt? Because are we talking about vt as the current value?
Yes. Wait, didn't you just say this?
No, like v hat is only on the left side and not on the right side. No, I mean like Yeah, the green underline that
Uh-huh.
should be v hat, but then the red should not be underlined, not have a hat. Shouldn't that just be vt and not v hat?
In terms of like, we consider everything as an estimate, right? Because you don't actually know the real value of like the environment, so that's why we have a hat on everything.
Okay,
That
so
makes
it's
sense.
the expected value.
Yeah, exactly. Yeah. Yeah. Right. So you incrementally update the value with some learning rate, right? We saw learning rates back in when we were doing backprop. All right. So I find it helpful to break down equations like this. So again, you have your TD error, your reward at your current time step, some discount factor between 0 and 1. This is the value of the next time step, and then minus the value of your current time step. And then you take that TD error and you update your value. So you take this value at your current time step and you add the learning rate times this TD error, and then that gives you the new value of this current time step. So that's the whole algorithm. And now we're going to apply it to the actual problem we just talked about of predicting when the reward will come. Cool.
So Lucy, it might be worth making a connection to previous lecture saying, like, this is equivalent to what we talked about. I have a current state, and I took an action. So based on the action, I got some reward, and I made the prediction. Then I'm going back and changing the current state's actual value. I'm
Exactly.
updating the current state's value.
Right. Yeah, so this is basically telling you what the value of each state is, and you're learning that, right? Just like how you can learn the value of actions. But right now, we're not going to talk about actions. All right. So let's apply this to the example that we talked about. So if we take time and we sort of chop it up into discrete time steps, we can sort of take this whole trial. This is just one trial of the experiment, and have these different time bins. Okay, and so what we're going to do is we're going to step through these equations for every time step and every trial. So we're going to calculate the TD error and then update the value, right? All right, so I find it helpful to make a chart like this. Okay, so this is T for T every time bin here, every time state. And then at 5, there's a reward, right? So the reward here will always be 1. And then here I've just set a couple values. So gamma will be 0.9 and alpha will be 1. And if you're following along, well, you should follow along because there's going to be a question coming where I ask you to fill in the blanks. So, all right, let's start. So at the first time step, there's no reward, right? So there's 0. And then you add gamma. And then you multiply by the value of the next time step, so v of t equals 2 here, and then minus v of t equals 1 here, right? So all value just assumed to start out as 0, okay? So what does this equation give you? 0, right? That's kind of boring. Okay, so TD error is 0, and then the value, of course, when you update it, is also 0. Good. Now, for state 2, it's the same thing, right? Because nothing interesting is happening. Same thing for state 3. Same thing for state 4. What happens when you get to state 5? Oh, look, there's a reward. So what happens here to your TD error? Now you have 1 plus 0.9 times. So if you imagine there's like another state that happens after this, you can just say that this is 0, right? Minus 0, right? So then what is the TD error here now? 1. You see that? Because all this is 0. Okay. So that's 1, right? And that makes sense given what we saw about the dopamine neuron firing when it wasn't predicted. Right? So that's what's happening here.
Let's go back to 4, Lucy, if you don't mind.
4?
Yes, please. So the predicted VT of 5, you're assuming that this isn't conditioned, so like your VT equals 5 is still going to be 0, not 1?
Yes, because you've never experienced
So this
anything
is
before.
the Q for the first time.
Exactly.
Okay, cool.
Yeah. Cool. Oh, and then you use that TD error here, which you got as 1, to update your value, which is now 1. Got it? All right. Now that was just trial 1. Let's do trial 2. All right, so again, the first couple of rows are pretty boring. They're still 0, 0, 0. What happens at 4 now, though? So the reward is 0. Gamma is still 0.9. But now what is the value of t equals 5? 1. Okay. And then value of t equals 4 is 0. So what do you get here for the TD error? 0.9. You see that? Because it's 0.9 times 1 minus 0, you get 0.9. Great. And then you update the value for 4, and you get 0.9. See that? All right. Now you experience the reward again on trial 5. So the reward is still 1. Again, same thing. This is 0. Minus, now the value of t equals 5 is 1. So now this TD error on this trial is what? 0. Because you've learned to fully predict the reward on this trial, right? Because the value of the state is 1, the reward is 1. Great. Now, did you notice what happened here? The TD error went from here to here. Now we're going to keep going. So trial 3, same thing, etc. Okay, but now for state 3, reward 0. Oh, I guess I just showed you. But anyway, if you plug this in, you have the value of state 4. So that's 0.9, right? 0.9 times 0.9 is 0.81. And then minus, this will be 0, right? So now the TD error here is 0.81. And you update that, and the value of state 3 is 0.81. And if you keep going, now you'll realize that the state 4 is fully predicted by its value, so the TD error is 0. Value is still the same. For 5, you get the reward, but the prediction error is 0. And there you go.
Sorry, one more question. Why is the TD error 0 for state 4? Can you just go back to the
Yes.
a very quick second?
So you have value of state 5, right,
Yep.
which is 1, times 0.9.
Oh, got it.
0.9
Okay, yeah.
minus the current value of state 4.
Got it. Thanks.
Yep. Everyone see that? Great. I love the nods.
I mean, Lucy, maybe it's worth just qualitatively mentioning it's because at state 4, you've already learned that you're kind of on your way to get the reward.
Yeah,
So there's no more surprise. You already kind of
Exactly.
know once you get to 4.
right. Now this is all working out really nicely because I've given you a learning rate of 1, right? So can you guys think of what might happen if your learning rate wasn't exactly 1? If it was less? If it was like 0.1, for example?
You wouldn't get the right result on the first pass. Like every time you go, you would get closer to the correct.
Exactly. So every time you update each trial, it would just take you longer to learn the correct value of each state, right? But eventually you'd get there. Great. All right, so here comes the quiz question. So what would you fill in for these two? The TD error and the value for state 2. I'll give you a second to look at this slide, and then you can put it in on the next, the poll everywhere. All right, you got it? Okay. And you try to put it in. I shouldn't have released it as it goes. Someone didn't round. All right, great. Well, if you put that in, that is correct, 0.729. let's go through why that makes sense. So you have, you'd have a value of t equals 3, right? 0.81 times 0.9 minus 0, right? So it's just 0.9 times 0.81, and that's 0.729. Great. Awesome. All right, and then finally on trial 5, the reward prediction error is now 0.656 at state 1. And now you filled in the values of all these states, right? So can someone tell me some observations about what happened over the course of learning?
Over the course of learning, the errors became 0, and then the values had that same the gamma to the k expression.
Okay, great. So one thing is the values reflected the discounted future rewards, right? So that's why they're smaller at t equals 1, but then they increase to t equals 5 because the values as you're approaching the rewarding state is increasing. Okay, and then you said the reward prediction errors are 0, but that's not exactly true. How did they change? What'd you say? They decreased, okay, as they went back. Okay, but also how did they move? Up, right? Up in time, right? So does this make sense now? So you have the reward prediction error, which when the reward was not predicted, it happened at t equals 5. But over the course of learning, the reward prediction error actually shifted to t equals 1, right? So that's very similar to what actually happens in the dopamine neurons. And I'll show you that again. Do you have a question?
I think in your original example, you sort of showed a spike, the anticipation, the spike occurring before the actual reward. Is this sort of suggesting that kind of the intensity of that spike also kind of widens out over time?
Like at the cue?
Yeah, yeah. Prior to the cue, I think.
Prior to the cue.
Right after the cue.
Or no, I'm sorry, yeah, right after the cue.
So, yeah, that would be, I'm not exactly sure if that's true empirically. I don't know if that, difference can be really seen.
Was the graphs that we were seeing earlier a measure of this value function here, or was it of something else?
Oh, you tell me. So what was the activity of the dopamine neurons? Did it look more like this or more like this? I can show you again.
It kind of looked more like the second column, yeah.
Exactly, right? So that's why when we talked about dopamine being the reward prediction error, so a reward prediction error is actually a kind of TD error, right? So dopamine neurons here are actually, the hypothesis is that they're encoding this TD error. That's pretty cool, right? So I'll just show you a little animation of the calculation that we basically just did, but now in video form, right? So here's the cue, and then these are the time steps leading up to the reward. And yeah, that's probably what you had during spring break. But yeah, you can see right here, right? The value is kind of increasing over time backwards, just as we saw and updated. And now the TD error went from here, that the time of reward is now moving backwards to the time of the cue. And now by the end of learning, as the trials go on, the TD error has now moved to the cue instead of the reward, exactly like dopamine neurons. Amazing. All right, a couple more notes on this. So you can actually decompose this equation and look at it graphically, and I think it gives another kind of intuition. So remember, this is the equation. And if you look at the value of v of t, and you plot it, you'll see what we just saw in the previous video, right? It's kind of like a little ramp up to the reward, right? And now v of t plus 1 is it looks basically the same, except it's shifted one time step, right? And now if you take the difference between vt plus 1 and v, you get this sort of derivative-like looking thing, right? Because The only differences between these two things are at this little boundary where there's like a shift in time, right? And gamma is usually very close to 1, and so this is what you get, right? Now, if you consider that in many experiments, like the reward comes right here, and then if you add the reward to this equation here, then these two things cancel out, right? And so that's what you get. The TD error here is just one positive spike. And that's also why if the reward doesn't come, then what you actually see is a dip, right? Just like this would predict.
So like when going through the trials again, at the last time we had like the prediction error at 0.656.
Mm-hmm.
But then if we go through one more trial again, that prediction error will become 0. Right?
Is that true?
Because then isn't it the gamma at, isn't it 0.729 times 0.9 minus 0.656, and the reward is
Gamma times V of t. It's 0.9 times 0.729, minus this. Yeah, I guess that's true. I think that you can think of it as like the Q is always an unpredictable signal. So like on every trial, the Q doesn't occur at like the same time, right? It's like kind of, there's some jitter, right? That's how you make a good experiment. And so the fact that the Q is now like the unpredictable thing, right? You still always have like a sort of like a burst of surprise, but that Q predicts now the reward that's coming. Does that make sense? Yeah. All right. Okay, yeah, so these are the 3 key features of the data that I pointed out, right? So the TD error at the Q, nothing at the reward, but also when the reward is emitted, there's a dip, right? And these are the 3 things that we see in the actual data. Great. Any questions on this? Mm-hmm.
So dopamine is related to the error, not to the value associated.
Exactly. Yes.
Good summary.
That's basically the summary.
Okay.
Go home now. No. Okay, great. Okay, so that was the TD learning algorithm applied to a very specific kind of experimental trial where there's a queue, there's a bunch of time that happens, and then reward, right? But this can be applied to many different kinds of situations. And one particular environment is like a maze, right? So a lot of reinforcement learning tasks are just like these grid worlds is what they call them, and they train an agent to sort of navigate through this maze or this grid world. And so if you can define rewards, then the agent will learn to basically navigate through this grid through TD learning. Right? So what is reward? Well, you can say that the reward at a goal, like this piece of cheese, is plus 20. So it's like really highly rewarding. But then the cost of each step, so that can be like a negative reward, that would be minus 1, right? And the reason you do that is because you don't want like the mouse to just wander around like into infinity. Like you want every step it takes to cost something so that it'll find the shortest path. So this is just like a little animation of this in progress. So you can see that every time it reaches the goal reward, it updates the value of the surrounding states a little bit. And then eventually, it will find a value like path, basically, through the states to the goal. Yeah. All right. So here's just some takeaways from TD learning. So like I said, this is truly remarkable because it's one of, I think, the most successful marriages between reinforcement learning and neuroscience. And this field of research is really booming, and there are a lot of people here at Harvard that are looking into this, my PI included.
Two things. The first one, like in the video that you just showed, there was, I think if I saw it correctly, there was like a step where there was one higher pixel at the top and like two sort of dark pixels at the bottom, but it still went to the dark pixel. There's like some like noise in the model to make it better. And the second question is like, if the dopaminergic neuron is modeling your TD error, what's the actual, like, do we know what the biological substrate of the value is?
Oh yeah, great question. So for the first question, yes. So that sort of just depends on how you choose your actions. So on Monday, Venki told you towards the end of the lecture, and we're also going to explore this more in section, the differences between greedy, epsilon greedy, and softmax policy. So that determines how you actually select actions in environments. So sometimes you're not selecting actually the best action in order to like explore the environment more. And then where is value? I wish SJ was here.
Thumbs up.
You didn't figure it out?
No, I'm still reading.
SJ did his thesis on reinforcement learning in the brain, so you guys can ask him when he's back. Actually, he's at a conference right now that talks all about reinforcement learning in the brain. So, I don't know, is there like a textbook answer to that?
I mean, there's no real answer, but you can imagine based on the formula, somewhere you're taking differences, right? So you're going to have calculated value functions when you're taking the errors. So maybe some upstream areas that has the value, then that gets subtracted out by some converging circuitry, right? So it's thought to be somewhere in this striatum, but exactly where upstream of the dopamine neurons is being worked out.
Yeah.
But you've also hit upon a question of going from a theory to say, I have a parameter.
Where is it?
Signatures of that
Right.
in
Where is it in the brain? Right. And so I think this highlights like a really great example of why theory is useful in neuroscience, right? Because if people didn't know about this TD algorithm, they wouldn't know to think about it when they saw this data from dopamine neurons, right? And this has inspired many other hypotheses in the field, sort of like an interplay between the two fields. Right, so I said it was developed in absence of any knowledge about these dopamine neurons. And so this unplanned correspondence suggests that this TD error dopamine parallel captures something significant about the brain reward processes. And TD error has some advantages. So it can distribute credit for delayed rewards, right? Because it's basically taking the reward at the end of learning and then distributing to all the states in front of it. It updates these values even before receiving a final outcome. And there's no need to remember the history or the structure of the environment. And it's computed on a moment-by-moment basis based off of the changes in value. All right, so you guys may have seen in maybe media that over the years, starting in 2015, there's been a series of, I guess, Nature papers and the covers of the Nature magazine of these different reinforcement learning networks that have been trained to learn these different games, right? So there's Atari that came first, and then it beat a human in the game of Go, and it beat someone in chess, and then StarCraft, and now there's sort of new ventures into understanding other kinds of reinforcement learning, particularly called distributional RL. And in all of these applications, TD learning or some kind of variant is used.
So in terms of the dopamine spike, what would happen when they first not learn like this cue corresponds to the reward? How would the spikes look? Would it just be like concentrated at the reward and then slowly move as if we were seeing like in the table moving back?
Exactly.
Okay.
Yeah. All right. So how does this fit into how the rest of the brain learns, right? Because this TD error is just like one signal. Like how can it possibly influence like literally everything, right? So I just showed you a very clean picture of dopamine and TD and how they're like very similar, but it's not exactly super clean, and the way that you map this onto the brain is also sort of work in progress. But the basic idea is that here, like I told you at the beginning, you have dopamine neurons in the SNC and the VTA, and they project to all different kinds of places. But there's a large density of them that project to a structure, a basal ganglia structure called the striatum. Okay, so that's here. And it's thought that the striatum is a structure that keeps track of the value of states in the environment as well as actions. Like, what are the best actions to take in each environment, or in each state? Right, so I said that. And the striatum also receives information about the environmental state from the cortex. So the cortex holds the sensory and the motor areas of the brain. And it has that information. It sends it to the striatum. And the striatum takes that information and integrates it with the reward prediction error information from the dopamine neurons. And together, this influences how value of states and actions are being computed. Okay, so the cortical neurons project onto what are called medium spiny neurons in the striatum. So that's like about 90-95% of the neurons in the striatum. And these neurons are thought to do these kinds of computations, updating the values, updating the actions. And then the striatum then outputs the selected, like it selects some action, right, and then outputs it through these other structures, and then executes the action because it sends the information back to the cortex to then execute an action, whether it's like a motor action or like a decision that has been made. And so it's like a loop, right? And there are other kinds of reinforcement learning algorithms, one particular called Actor-critic, where people have proposed a very fine-grained mapping between the actor-critic, what is the actor, what is the critic, and then the structures in the brain. So I'll break it down for you. So here the idea is that there's an environment, and there's states or stimuli that get inputted into the brain and then the striatum, and there's two different compartments, I guess, of the striatum. Right? So there's one called the actor, and the actor is the one that learns policies. So the actor actually chooses which action to take. Like, for example, the mouse in the maze, it's what tells the mouse which direction to step in for this time step. Right? But then there's this other compartment called the critic, which evaluates whether the actions that the actor took were high or low in value. Right? So if the mouse took a direction in this step and then it didn't get anything, then it said, well, I'm not sure if this action was great. If it takes another step and maybe gets closer to the reward and eventually reaches the reward, then the critic will say, oh, actually, those actions that you took were pretty good because it got you to reward. Right? And it's critical because this is pretty cool because the TD error here goes into both compartments and updates them in a different way. And then they also both interact. So the critic tells the actor then to reevaluate what it does next. And so people think that the actor in the brain maps onto the dorsal striatum, so the dorsal meaning the, I guess, top part of the striatum. And this area is seen to influence a lot of action selection. And when you lesion this area, you actually get lots of deficits in action selection. Whereas the ventral striatum, in contrast, is where they think that the critic lives. And because this structure does a lot more like reward processing, assigning value to different sensory inputs, states. And so this, like the question was asked, where is value in the brain? Well, this might be a candidate place to look, right? And then dopamine, which we think is like the TD error, right? This also modulates synaptic plasticity in both the dorsal and the ventral striatum. So this is like one proposal for how things might be mapped onto the brain, right? But again, things are not super clear-cut just because like we make up like a nice image and draw parallels and stuff. So very much ongoing research.
So this actor-critic model is used to describe the brain right now?
It is. I would take it more as like an analogy, let's say, yeah, or like a particular hypothesis, because the actor-critic algorithm is used in a lot of reinforcement learning systems. For example, to like train those networks that played games, right, against other people. Yeah. All right. So for the rest of class, we're going to talk about a pretty cool application of this TD algorithm idea to disease, particularly addiction. And so there's this paper that I actually really like, published in 2004 by this guy, David Redish. And he studied how TD reinforcement learning could be used to model the addictive processes in the brain when you're exposed and get addicted to drugs. So here's a reminder to not do drugs. And we can ask the question here, why are drugs so addictive? Anybody have any ideas? Why is anything so addictive? Aw, you already gave it away. He said prolong the effect of dopamine in the brain. How come some things are addictive and other things aren't, right? Like other pleasurable things, right? Mm-hmm.
Well, some things, like drugs, make us more happy.
Like more happy than usual? Than other things. I see. All right, so they make you abnormally happy. All right.
Like, it is kind of like it makes you abnormally happy because it floods your brain with dopamine, but then you get used to it. So instead of getting a better reward than you expect, you're just going through your day going, this sucks. There's no more dopamine. I'm expecting it to be better than it is.
Exactly. Yeah, very good. Any other accounts of what it's like to be addicted?
That's not good.
Not that I'm addicted or anything. This question's hard to follow, but I think it's because the other chemicals in your brain and your body. Because some people can take cocaine and not get addicted, and some people get addicted. Some people can drink an entire bottle of rum and not get addicted. Some people 3 drinks and they're addicted.
That is true. It's a very fascinating thing. I honestly don't know how to explain that, but I will say that, some of the things mentioned, like there's an imbalance, right? Like there's more dopamine than normal that you would get from anything else, like food or sex or anything else that's, naturally pleasurable. Although, cocaine is naturally occurring, but not in this amount. And actually, many drugs of abuse, like you guys already mentioned, they increase dopamine levels either directly, like cocaine, or indirectly, like nicotine and heroin. And yes, you guys got at this too. So cocaine produces a phasic increase in dopamine because of the buildup at the synapse. So looking here at like a normal synapse, you'll see that when dopamine is released, it binds to receptors on the receiving neuron, and then there's like a reuptake transporter that feeds it back into the neuron, right? But when you take cocaine, basically there's like cocaine floating around here, and it blocks these re-entry transporters here. So basically the dopamine is flooding the synapse here, and it has nowhere to go. So it just binds to all of these receptors, and suddenly you get this huge surge of dopamine that is more than you would get naturally. Because there's some mechanism for homeostasis, kind of similar to that. Okay, so Redish studied how this cocaine addiction could be modeled with this modified TD learning rule, which I'll show you in the next slide. So like we saw earlier, in normal TD learning, once your reward is fully predicted, your learning actually stops, right? Because now you fully know your environment, you know what's going to happen. But here his hypothesis is that cocaine induces an increase in the TD error that you actually can't compensate for by learning, right? So you never fully predict your reward, and that actually causes you to continually update your values. And so let's show this with like a very simple example. So imagine that, very similar to the situation we just saw in the other example, where you have a queue, and then after some time you get a reward, okay? And this is like the modified TD error that he proposed, which is the max of this normal TD error, as you see here, plus some D term, which is going to be the drug-induced dopamine surge. So the maximum of this term or just the D term itself. So whichever term is bigger is going to be the TD error. Okay. So what happens is that in natural rewards, right, your TD signal for the reward goes down to 0, and then your TD signal for the Q or the CS, it goes up, right? So that the TD error is only at the Q and not at the reward, right? So that's what it usually looks like. Now, because cocaine acts directly at the synapse, it induces this extra synthetic, surge of dopamine, which is what they're trying to capture in this D term, right? So what happens is that the TD error still decreases, but then it sort of plateaus at whatever you set D to. And then as a result, the Q, the TD error at the Q, it also keeps increasing to match whatever D is. And so the effect of addictive drugs is to produce a positive TD error independent of the change in the value function, right? So now the difference between the value and the predicted value is, even if this is 0, the TD error is still going to be positive, right? And this makes it impossible for an agent to learn a value function that will cancel out the drug-induced TD error. So what you get is just a perpetually positive TD signal. And remember, because you're updating the value with the TD error on every trial, what happens to the value if TD is always positive? Goes up, 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 and away, right? Okay. So in addition, even though you still get like the shift of the TD error to the Q, because cocaine acts directly at the synapse, then you also get like a burst at the reward as well. So it's like what they call a double dopamine signal. Okay. So this is kind of like in a similar example to what we talked about before. But now let's try to apply this more to like a natural-ish scenario where you can either eat food or have cocaine, right? So this is a real experiment. So when rats are given a choice between cocaine and food, the probability of, it's not like they're just going to select cocaine every time, right? The probability of selecting cocaine depends on the amount of food available, right, as an alternative, and also the cost of each choice, right? So how hard is it to get the food or the cocaine, right? So if I give you like a ton of food, then you're like, okay, actually maybe that sounds better than like the cocaine. Now, in other studies, when humans are given a choice between cocaine and money, they actually decrease their cocaine selection if you increase the monetary incentive. So when people like try to rehabilitate cocaine use, in the past they've used like monetary vouchers as incentives, right? But obviously, if you are a very experienced and long-term user, that's not really going to have that much of an effect on you. So in this paper, they modeled it something like this. So, there's on each trial, you can choose an action. You can either choose to get food or to get drugs. And there's some delay, and then you get the food or you get the drug, right? And then they varied the value of, they varied the reward of the food, but then kept the reward of the drug as 1. Okay, so this is 1, and then the reward of the food, it ranges from 0 to 3. Okay. So here on the x-axis is the value of the food, which is the contrasting reward. And on the y-axis is the probability of choosing the drug, right? So you should maybe expect that if the food is of higher value, then you might choose the drug less, right? So we might expect this kind of relationship, okay? Okay, so that's pretty much what we see. And then the two colors are just actions that are like early in learning versus actions that are later in learning. Like the blue is later in learning, the red is earlier in learning. And this is for a drug surge or dopamine surge of 0.01 here. It's pretty low, right? Now, if you increase this D term, maybe up it a little bit to 0.025, you start to see a bigger gap where in the later trials, you actually have a higher probability of choosing the drug because now the natural rewards they're already fully predicted, and the value of the drug is actually increasing more and more and more. And if you then increase this even more, then you get an even bigger gap between the two. All right, so just like we calculated the TD errors for a cue and a reward, in section this week, you're actually going to do this for basically this paper, okay? You're going to pick a value of D. Well, I gave you a value of D. And you're basically going to do this and then make some observations about how this affects the TD error and the value of these 5 states. So that's it. Any questions? No?
Wait, so for the red curve and the blue curve on the previous slide, which one is which?
So these are all just like early trials and late trials. So late trials is kind of like when you've already learned the reward and you can already predict the reward. Now it's saying that you're actually preferring the drug more because the value of the drug continues to increase. Yeah, without bound. Mm-hmm.
Could you go back one slide, if you don't mind, Lucy? Sorry.
Oh, you mean this.
A little bit more. Yeah, this slide, perfect.
Mm-hmm.
I guess suppose 2 questions. The first one is something that I noticed it a little bit earlier, didn't fully understand. Why does your Q error plateau rather than, is it because like all the error from the reward is accumulated at the Q? And also like for the...
What do you mean Q?
Not
CS.
Q, CS.
Oh, the Q. Okay, yeah.
Right.
CS?
The Q signal, I suppose.
Uh-huh.
Like, why does it plateau at some value rather than continue to increase? Would it need to increase if you increase the magnitude of the reward?
Are you saying for this one or for this one?
For the top one.
Why does it plateau?
Yeah.
Why does the TD signal plateau?
Yeah.
Well, the TD signal is just, it's like there's no reason for it to increase after it moves to the Q.
So
right?
let's say like I have a reward of 1, and then suddenly you give me 2 bananas instead of 1, and I now have a reward of 2.
Uh-huh.
Like then that error would continue to propagate back to the Q.
Oh.
Right? And it would increase, right? Is that correct?
I guess so. Yeah.
Okay, cool.
Yeah.
Can you explain more on how the double dopamine signal is associated with reinforcing a recurrent behavior, like as in like addiction?
Yeah. Well, so the idea here is like, well, I mean, that's hopefully what you understand after doing the section exercise. But basically, why don't we think through it then? So remember how in the normal learning case, you have a value that's fully predicted by your reward, right? Think about what this equation does, okay? So let's say you have a reward of 1, and then a value of 1. And then now this term is 0, right? But then if you have a D of 0.5, then you're going to add 0.5. And then what is the maximum of 0.5 or 0.5? 0.5, right? So that TD error is going to be positive, and you're going to add to your value, right? Even though your value is fully predicted, right? So what's going to happen to the value over time? It's going to increase. And it's going to increase and never stop increasing, right? So the idea is that, at least their proposal, is that the reason that you become addicted to things is because it just gets better, right? Like the thing that you're addicted to just gets better. But eventually, I mean, the reason that this doesn't work, this model isn't perfect, is because usually you also have this adaptation effect, right? So there's still some learning, because usually addicts, like, you want more and more and more, right? In order to have that same like hit of pleasure. Any other questions?
Maybe thanks for listening.
All right. Cool. All right. We'll see you guys.